Welcome to our first video. This chapter is called Prerequisites for Calculus, and this video is basically covering the first two sections on what I deem the most important. So this video we're going to cover slope, the different ways we can write lines, and we're going to touch on functions, these main three things here. Alright, so this is a little graphic organizer about slope. And slope is definitely something that you already, should be pretty familiar with, so we're just going to touch on this quickly. The formula for slope is y minus y over x minus x, and we know that slope is called rise over run because this is the change in y, so it's how much we either rise or fall if it's negative, and running is the change in x, which means we're going across. The last way that you can write this, and the book touches on this, m is just slope, so the last way that you can write it is delta y over delta x. Delta is just a Greek letter, and it's represented by this triangle, and it means change in. So this is how much we change in the y, and this is how much we change in the x. So this is a third way that we can write slope. Okay, there are four types of slope, which we'll look at here. And if a slope is positive, that means as we read our graph from left to right, our line's going up, or our slope's going up. As we read our graph from left to right, it's negative if it's going down. So these are just the two examples of, this is the equation of this purple line here, 2x plus 1. We can notice that the b value, the y-intercept, is 1. That's where it hits the y-axis. And the slope is 2 because from any point to any other point, you rise 2 and run 1, which is 2. Then this negative slope here, this line that has negative 3 slope, we can see that the y-intercept is 2. It hits the y-axis at 2, and we fall 3 and run 1 to get to any from one point to another. So that's why the slope's negative 3. 0 and undefined slopes are as follows. A zero slope, move that, a zero slope means it's a horizontal line. So we don't rise at all, but we run. So it's like 0 over any number. This is the line y equals 3, a horizontal line. And an undefined slope means that we literally don't have a slope. It is undefined. That is any vertical line has an undefined slope. So this line is x equals negative 1. It's a vertical line through wherever x is negative 1. And this hoi vux, that's just a way that you can remember the difference between horizontal and vertical lines. Hoi stands for horizontal, 0 slope, and it's always of the form y equals a number. Vux is similar. V is for vertical, u means the slope's undefined, and it's of the form x equals a number. Then we have a few examples. So our first example is down here. We want to find the slope between 2 points. Okay, so let's zoom in on this rather. Okay, so we're going to use our slope formula, which is the change in y divided by the change in x. Okay, so our y values are 2 and 4. You can subtract them in either order. You just have to be consistent in the order that you subtract your x's as well. So if we subtract our y's, if I do 2 minus 4, then when I work my x's, so we'll do that with this color, the x's, I have to go in the same order. So since I started with this coordinate point here, I need to start at the same coordinate point with that x value. So negative 4 minus 6. All right, let's see what our slope turns out to be. In our numerator, we'll have negative 2, and in our denominator, we'll have negative 10, and that will simplify to a positive 1/5. Okay, let's take a look at another example. We have a linear equation, and this is in standard or general form, which we'll explore in just a minute. We want to know what the slope of that is. Well, in order to easily find the slope, we want to get our line into slope-intercept form, which is y equals mx plus b. So we want to solve this for y, so we can easily find out what the slope of this line is. All right, we want to get y by itself. So what we're first going to do is subtract this term. So we're left with negative 2y on the left-hand side. And then instead of writing 10 minus 3x, I'm going to write the two terms in the opposite order, so it looks like mx plus b. Now be careful, our slope is not negative 3. We have to first solve for y. So we're going to divide all three terms by negative 2. When we do that, we'll get y equals a negative over a negative is a positive. Keep it as a fraction because slope is most helpful as a fraction, so you don't have to change that to 1.5. And then we have opposite signs and we're dividing, so we'll get the negative 5 there, or minus 5. Okay, what we've done is we have written a line from standard form into slope-intercept form, and the slope is right here. Since this is now of the form y equals mx plus b, and m is the slope. The last thing I want to take a look at is, I just wrote it as a question mark because I figured we could just talk about it once we get there. And just as a quick recap, parallel lines, two lines that are parallel, have the same slope. So parallel lines, look like this. They're two lines that have the same slope. They're not the same line. They have different y-intercepts, but they have the same slope. And then perpendicular lines, lines that form a 90-degree angle when they intersect, those slopes are opposite reciprocals. So perpendicular lines look like this. And they form a 90-degree angle where they intersect, and their slopes are opposite reciprocals. Now, what does that mean? Opposite means that one's positive and one is negative. So if we start with if we say one of the lines has a slope of negative 2, which is not my drawing at all. Neither one of these lines has a slope of negative 2. I just made a quick drawing. But let's say that one of the slopes was negative 2. We want to find the slope of the line that's perpendicular to it. So opposite means that other slope would have to be positive, and reciprocal means we flip it. So this is really the number negative 2 over 1. So if we flip that, the reciprocal would be half. The opposite reciprocal would be half. So as an example, negative 2 and positive 1 over 2 are opposite reciprocals. So that's just a quick recap of some slope. Next, we're going to take a look at lines. Okay, throughout this course, throughout calculus, we're going to be dealing a lot with lines. Really, calculus has a huge amount of algebra in it, and so that's why we're starting with these prereqs for calculus. They're basically all the basics of algebra. So linear equations are those that make a line, literally has the word line in it, and there are three ways that we can write the equation of a line. You're probably most familiar with these two, and standard form your book calls general, just FYI. So point slope form looks like this. Y minus y1 equals m times the quantity x minus x1. This is most helpful for when you literally are given a point and a slope. I'm not even going to write that down because of how obvious it is. If you want to write it down, feel free. But again, this equation works best if you're literally given a point and a slope. Cool. Take a look at slope-intercept. Slope-intercept is what most of us will remember, probably the most. Y equals mx plus b. I'd say that this is normally how we will write our final answers. We can go from point slope to slope-intercept pretty easily. But this is solved for y. M is the slope, b is the y-intercept, which is why it is called slope-intercept form. And lastly, standard form looks like ax plus by equals c, where a and b are not 0. C can be 0, that's fine. Okay, let's take a look at point slope form. We'll do a quick example. Here's a quick example. We want to write the equation of a line that's perpendicular to this line. It's written in slope-intercept form and passes through this point, negative 18, 1. Okay, so some keywords here. Perpendicular. We're given the equation of a line that we want to be perpendicular to, and we're given a point. So secretly, we are given a slope here. We are given whatever the opposite reciprocal of this slope is, 3, which is negative 1/3, and then we're given a point. So even though we're not explicitly told, hey, here's the slope, we know that we can find the slope pretty easily because of this keyword perpendicular to. We're also given a point. So we're going to write this in point slope form. But first let's figure out what the slope's going to be, and we'll write out what the point is. The point's really easy. It's given. And then our slope is the opposite reciprocal of this slope because they're perpendicular. So our slope would be negative, and then the reciprocal of 3, 1/3, negative 1/3. Great, so let's fill out point slope form. Y minus y1 equals mx minus x1. All right, let's fill in. This is m, and this is x1, y1. This y and this x stay just y and x. So you're going to write y minus 1 equals negative 1/3 x minus negative 18, so plus 18. Okay, let's solve for y. We don't usually want to write final answers in this form. We want to write them in slope-intercept form, so we're going to solve for y. So let's first distribute our negative 1/3 through. And the negative 1/3 times positive 18 is negative 6. We're taking a third of 18, a negative third of 18 rather. Okay, so let's add 1 to both sides. When we add 1, this went away, and we'll add 1 here, we'll get minus 5. And there we have it. A line that is perpendicular to this line and passes through the point negative 18, 1. Notice that we did not care about the y-intercept of this line. When you see perpendicular or parallel, you only care about the slope. Okay, let's talk about slope-intercept form a little bit. M is the slope, and as I said before, B is the y-intercept. And then standard form, we did an example of standard form on the previous page where we solved for y. So I'm not going to get too far into standard form. It's probably the one you'll see the least, but if you want to work with a line at all, it's probably the most helpful for it to be in slope-intercept form. A last example that you may see is if you're given 2 points. And if you're only given 2 points, you need to first find the slope. Then you'll have a slope and a point. You can use either point. And we found the slope in an example on the previous slide. Functions is a very broad topic in math, and I am just going to barely scratch the surface of it here. But let's say, for example, we'll do the function f of x. We'll do a linear function. F of x equals negative 2x plus 5. This is the same as writing y equals negative 2x plus 5. They're both lines or linear equations or functions. This is just function notation, f of x. Something is a function. A relation between two variables is a function if for every input that you plug into the function, you always get the same output. You're not going to plug in 2 on Monday and get one number and then plug in 2 the next day and get a different number. So let's plug in 2. Let's evaluate f of x at 2. That means that I'm going to plug in 2 everywhere there's an x. So we'll have negative 4 plus 5, which is 1. So f of 2 equals 1. That means that on this line, when we plug in a 2, we get out a 1. Therefore, the coordinate point 2, 1 is on this line. That leads us right into independent and dependent variables. The independent variable is the variable that kind of does what it wants, right? It's whatever we plug in. So in this case, the independent variable is x. And then our dependent variable is our output f of x or y. That's usually how we'll deal with things. Now, sometimes we might have a different function. It might be called a of t, whatever. In this case, it's f of x, and the independent variable is what you plug in. So independent, that is the input, and the dependent variable literally depends on what you plug in. That's what pops out of the function. So in this case, our example that we did, our independent variable is x, and our dependent, our output, is y, or f of x, because it depends on what we plug in. All right, our domain and range. Domain are all of the values that your independent variable can be. Normally that's x. So it's everything that your independent variable can be. And our range deals with our output. Our range is what y can be. A lot of times we have zero restrictions on our domain, meaning, like, for example, this function here, this line, there's no restrictions on what can be plugged in for x. We can plug in any real number that we want. And there's also no restrictions for y. Our range has no restrictions. So in this case, in this example, our domain is all real numbers, which we can write as this fancy r, or we can write it as literally everything from negative infinity to positive infinity. That's interval notation. Our range is the same. All real numbers, or from negative infinity to positive infinity. And any line, any linear equation that's not horizontal or vertical will have this domain and range. We're going to explore in the next slide some restrictions on our domain or range. Okay, let's take a look at domain and range graphically. So I picked a circle and then a square root function. Let's take a look at the circle. This is not a function because if we plugged in, let's say 3 to our function, we get an output up here at positive 4. But we also get an output down here at negative 6. So if we plug in 3, sometimes we might get a 4, that's on our circle, and sometimes we might get a negative 6. So it's not a function. It also doesn't pass the vertical line test. Any vertical line that I draw can only hit a function once. In this case, this vertical line here hits more than once. It hits our graph more than once. So anyway, this is a circle. It's not a function, but that doesn't mean it doesn't still have a domain and range. So let's take a look at what our domain would be. Our domain is all the x values that our circle takes on. Looks like the leftmost x value that our circle hits is out here at negative 2. And our rightmost is 4, 5, 6, 7, 8, out here at 8. So we'd say that our domain, and it includes negative 2, and it includes 8. So we're writing that as an interval from the smaller x value to the larger. We're using brackets because our function, our circle takes on the x values of negative 2 and 8. Our range, we look in the y direction vertically. So our lowest value for y is negative 6, and our tallest value or highest value for y is up here at positive 4. So our range, our circle actually hits those values of negative 6 and positive 4. So again, we use those brackets. This circle, unlike a line or something that has an arrow in it, this circle does not extend indefinitely in any direction, so there's no infinities here. Let's take a look at this guy over here. This equation, well, rather this function, and it is a function, it passes the vertical line test. This is actually the square root of x plus 4. And if you put that into your graphing calculator, you would see this right here. I didn't ask you to do that for this because it's a lot more difficult to graph a circle, as you can see. So y equals the square root of x plus 4 is much easier to plug in. This is a function, like I said. Let's take a look at the domain. So we're going to look from left to right. And our leftmost value that we hit is negative 4, and we actually don't have a rightmost value. This extends indefinitely to the right. So our domain we take on -4, so we're going to include it, and we actually extend to infinity. Infinity always has an open parentheses rather than a closed bracket because infinity cannot technically be reached. Let's take a look at our range. So we look vertically here. So our lowest value is y value down here at 0, right? We're on the x-axis, our y value is 0. And even though this looks, like it's going upwards very slowly, and it is, it actually is going upwards forever. And so we are going to take on all y values 0 and greater. So our range, we start with our lowest y value of 0, and that arrow extending upwards means that all of the y values will be taken on in that positive direction. So we're also extending towards infinity, and once again you need the open parentheses for that. We will explore domain and range a little bit more throughout the year as we see it, but it is just important to understand domain more so than range. But domain means, hey, what can we plug in that will give us an output? So I can't plug in any values that are less than -4. I can't plug in -5. It's not a part of this function here. If you tried to plug in -5, you'd have a negative value underneath your square root, and that doesn't work in the real number system. So domain's very important because we need to know what we can and cannot plug into a function or a relation. The last thing we're going to take a look at are piecewise functions. And a piecewise function is just a function that's broken into pieces. So again, a lot of things in math are named exactly like with what they are. Not a lot of creativity in the names. Let's take a look at this first example. This one is already graphed. I just found it online. It's a pretty good one because I like it because it has a lot of different types of functions. We can see there's part of a parabola here, a quadratic. And then there are 2 linear functions here. This one's horizontal, and then this one has a positive slope. But as you notice, there's not any like overlaps, and what I mean when I say that is like the parabola extends indefinitely left. So if we look left to right, the parabola takes on all these x values from -infinity up to where x is 1, and then the parabola stops. And then this horizontal line, this linear function here, starts just to the right of when x is 1, that's that open dot, and goes to when x is 2. And then this last linear function, this line here with a positive slope, begins just to the right of 2, that's that open circle again, and then all the way to positive infinity. So there's not any values of x that are not accounted for, right? All values of x are accounted for. So let's write out what this piecewise function would be like written out here. Let's take a look at it. We see that there's 3 pieces, so we're going to start with this big bracket. So it's already called f of x, so we'll start this big bracket, and there's going to be 3 different parts. So we're going to have to write what those functions are, and then a little comma. And then I'm just going to start with the second part of the piecewise over here, and that is telling us like what the x values are for each piece. So this first piece here, this parabola, goes from when x is -infinity all the way and including when x is 1. So the way that we'll write that is that's all values when x is less than or equal to 1. The second part is x values between 1 and 2, not including 1, but including 2. So x is smushed in between 1 and 2, and we're including 2. We're not including 1 there. 1 was included in this piece, closed dot. And then the open dot, it's not included. And then we're including up to 2 and including 2. This last piece is 2 and not 2, but everything greater than it, that open dot there. So we're not including 2, but we're including everything greater than 2. So just to the right of 2, 2.00001 would be included down here. So that open circle and then to the right. Now we need to write each equation or each function. So this is just a regular old parabola, just x squared. Its vertex is down here at 0, 0, and it's not like skinnier or wider than any regular parabola. So this is just the function x squared. Then this function here, this line, remember hoi vux, so it's a horizontal line, so it's y equals, and this is the line y equals 3, so y equals 3 goes there, because no matter what, the output's always 3. And then let's figure out what this line would be. If we extended it, it would hit the y-axis at 0. So let's find its slope. We'll go from point to point. We rise 1, run 1. We rise 1, run 1. So our slope is 1. So it's y equals 1x plus 0 if we thought about it in slope-intercept form. So it's 1x plus 0, which is just x. So this is the piecewise function for this graph here. And I didn't need as much space as I put here. This comma could be right after those three, but that's fine. So this is what a piecewise graph looks like. No jumps or gaps between the x values. So that leads us into what the absolute value function is. Absolute value makes a v for value, and this is the parent graph of an absolute value function, meaning it's like the simplest one. And this is actually a piecewise function. Let's take a look. It's actually two lines. There's this line here that is from when x is negative infinity all the way to when x is 0. It has a downward slope, a negative slope. And then as soon as x is 0 and all the way to infinity, it's a positive sloping line. So it's actually two lines, and they're separated at 0. So this piecewise graph is going to have two pieces. It's only going to have two pieces. And the first piece exists when x is less than 0. And the second piece exists when x is greater than or equal to 0, because that's where our lines switch. We have a negative sloping line, and then at x is 0, we switch to a positive sloping line. So what is the equation of this line? Well, this line has a y-intercept of 0 and has a negative 1 slope. So that is the line y equals negative 1x plus 0, or just y equals negative x. Then this line also has a y-intercept at 0, right? They intersect here. And it has a positive 1 slope, rise 1, run 1. So 1x plus 0, or just x. This is actually the definition of absolute value. So you should definitely have this written down. This is the definition of absolute value. It is a piecewise function. And so that's why piecewise is important. A piecewise function is just a function that's broken into pieces. That's all. However many pieces, usually we'll see ones that are 2 or 3 pieces. That's pretty much it. And then an absolute value function is a specific type of piecewise function that forms a v.